Hello and welcome back to the lecture of time series econometrics. In the previous lecture, we have derived the roots of AR characteristics polynomial equation. Now, in this lecture, we are actually going to sort of uncover the relationship between phi 1 and phi 2 that we got in the roots of the AR characteristics equation. Now, to do that, we will actually use the property of invertibility. And before we actually do that, let me again write down the AR characteristics polynomial equation using the lag form. So what it means is my AR characteristics polynomial equation would be 1 minus phi 1. I'm using lag form here. L phi 2 L square equal to 0. Now, when I want to actually when I actually convert the AR characteristics polynomial into MA characteristics polynomial, I need to use the property of invertibility. Now, why do I do that? Now, that's a very interesting question. Why I'm actually going to do what I'm going to do is that the moment you invert AR characteristics polynomial into MA characteristics polynomial, you're assuming few things. You're assuming certain kind of structure of the value for theta 1 and theta 2 and the relationship, and that is actually very important because, as I said, in the case of higher order AR or MA model, you assume stationarity first and then you derive the series. It is not on the other way around. It is not that you actually write down the series and then you run for finding out the stationarity condition, but you rather assume the conditions of stationarity and then you derive the series. Okay, so just using that, keeping that thought in mind, we are actually going to see how this value of theta phi 1 and phi 2 would be. Now, first thing is we are actually to sort of do the invertibility. What we are going to do is we're actually going to take L common. So basically I'm going to write L square L to the power minus 2 phi 1 L minus 1 and phi 2. I just explain in a moment why I'm doing what I'm doing. Now, now I'll sort of use a different sort of variable that will represent my L inverse. So let's write down lambda. Lambda is equal to L inverse. So remember in the previous case, we actually wrote x equal to L. So we basically replaced L with x. But here we are replacing L inverse with lambda. Okay. So then this equation would look like lambda square phi 1 lambda minus 1, right, is equal to 0. So like in the previous case, we can basically write lambda square minus of phi 1 lambda. Sorry, here I had to write phi 2. Phi 1 lambda minus phi 2 is equal to 0. Now, if I obtain the root here, again, like we did in the previous case, our roots would be, let me again write down, roots would be minus b, which is now phi 1 plus minus b square, again phi 1 square plus 4ac. 4ac is 1 phi 2 by 2a, which means here I have a is 1, right? So I have only 2. Now, in the previous case, when we used the roots for the AR equation, when we didn't really convert it, so we had the value of the roots, modulus of the value of the roots had to be greater than 1, right? Now here, since I have taken an inversion of that, so that means the modulus of the value of the root should be less than 1, right? So I'll write mod of these, or I'll write separately maybe. I can write mod of these phi 1 plus minus phi 1 square plus 4 phi 2 by 2 has to be less than 1, okay? And that is because the roots are now, I have taken an I have actually inverted the roots, right? So if I actually derive this, if I actually sort of obtain the value of the root, so it will mean, so I can actually write minus 1. So the roots are going to be phi 1 plus minus phi 1 square plus 4 phi 2 by 2. This should be the this inequality relationship, right? So now what I can write is, I can write minus 2. So I can actually write like this: phi 1 minus this value plus 4 phi 2 by 2 is, this one is less than phi 1 plus phi 1 square plus 4 phi 2 so plus 4 phi 2 by 2 is, oops, not by 2. So if I'm writing, or I can, if I'm, okay, let me just write down, this is 1 as I wrote, is greater than, is less than 1, right? So now if I just use each of this inequality, so what I'll get is, I'll get, first I'll get minus 2 is greater than phi 1 minus phi 1 minus phi 1 square plus 4 phi 2, right? And if I square both the sides, so what, so basically I can take the phi 1 on the right hand side, on the left hand side, and what I'll get is, so I can basically write 2 plus phi 1 is greater than, by taking the minus sign common, right? Like basically phi 1 square plus 4 phi 2, okay? Now I take square of the both sides, so basically what I'll get is, what I'll get here is, if I take square on both the sides, is that 4 plus 4 phi 1 plus phi 1 square is greater than phi 1 square plus 4 phi 2, which means you can basically phi 1 square gets cancelled, and then you have 4 on both all the terms, so which means you have, you can take 4 as common, so you will have, so 1 is greater than phi 2 minus phi 1. So that's one condition that you derive from this for the relationship between phi 1 and phi 2 for the AR2 model, okay? So let's write down equation 1. Now we'll use the other inequality where we wrote phi 1 plus phi 1 square plus 4 phi 2 by 2 to be less than 1, which means you can basically phi 1 plus phi 1 square plus 4 phi 2 is less than 2, or you can take square of phi 1 square plus 4 phi 2, and on the right hand side you will have 2 minus phi 1 square. So let me use a separate space. Let me just put an arrow here so that there is no problem in understanding. So here I will have my phi 1 square plus, so I'm taking square on both the sides, okay? So plus Oh, I should have used. Maybe I should use the same color. Um, so I will have phi 1 square plus 4 phi 2 is less than 4 minus 4 phi 1 plus phi 1 square, right? Plus phi 1 square. So which means I can easily cancel out phi 1 square, phi 1 square from both the sides, and in the same manner I can actually have 4 common phi 1 plus phi 2 is less than 4. So which means I will have my phi 1 plus phi 2 less than 1. Okay, so this is my condition number 2, right? And then we already have phi 2 mod of phi 2 less than 1 for AR2 series to be stationary. Like we have seen in AR1 series, mod of phi 1 needs to be less than 1 for the series to be stationary. In case of AR2 series, we need to have mod of phi 2 less than 1 for the AR2 series to be stationary. So that is the third condition that we need to add here. So that is mod of phi 2 has to be less than 1, which is our condition number 3. So these three conditions are to be satisfied for AR2 series to be stationary and the roots of the AR polynomial to be real.